Okay, good afternoon, everyone. Today we are pleased to have Dr. Andrej Risteski as our webinar speaker. Andrej is an associate professor in machine learning department at Carnegie.
Assistant.
Okay,
Assistant. Not yet.
okay, soon. On the track, associate professor. Okay, he received his PhD in computer science at Princeton. And he's the recipient of an NSF Korean Award, Amazon Research Award, and a Google Research Scholar Award. Andrej's research areas across multiple Andrej's research lies across multiple areas, including generative models, representation learning, natural language models, out of distribution generalization, AI for scientific applications, sampling, and optimization. More broadly, he aims to develop principled and mathematical understanding of statistical and algorithmic problems arising in modern machine learning paradigms. Without further ado, Andrej, the stage is yours.
Well, thank you for that kind introduction, Sophia, and thanks for the invitation. So today I'm going to tell you a little bit about the kind of sequence of works that's loosely around trying to understand some statistical and algorithmic trade-offs around what I call score-based losses. This is like a kind of family of approaches used to fit different types of generative models. This is joint work with a bunch of great folks over the last couple of years. I'll tell you a bit more what these kinds of losses are and why I'm interested in them in the course of the talk. So unless you've been kind of living under a rock, you know that in the last even less than a decade, generative models have made huge strides. When I was a grad student, GANs were the big thing, and myself when I was a PhD student and a bunch of other people were kind of very impressed about how GANs can do these kind of cute tricks like extracting style and making Mona Lisa look like it was painted by Van Gogh, as well as these kind of in-painting things where you take Nicolas Cage and put it in Superman. And then, what still seems like a century ago, the first version of DALL-E came out, and we were all kind of shocked that it could produce reasonable outputs to sort of relatively strange inputs, like, armchair in the shape of an avocado. And then nowadays, models like Midjourney can do some truly impressive things, like, generate a picture of Abraham Lincoln, taking a selfie on a beach. So I'm going to focus on one kind of basic ingredient in the pipeline of generative models, which is, I'm sure, not new to many, if not most of you, which is learning and distribution from samples. The kind of general setup here is relatively straightforward. You imagine that you have some training data, let's say x1 through xn, coming from some ground truth distribution p star. You pick some parametric class of distributions that you're going to try to fit these samples to. So let's say, some class of distributions p theta for theta lying in some parameter set capital theta. Then you have some kind of algorithm that tries to in some way select the best theta in this class. This gives you sort of some kind of model that's supposed to be approximating the distribution. And then what you're going to do with this distribution is you're going to draw new samples, again, via some choice of algorithm. And hopefully these samples look like some new samples from the distribution you were learning from. So maybe like, new pictures of puppies. Okay, so of course there's many different ways to kind of operationalize different parts of this pipeline. This is a stats crowd, so perhaps the most kind of classical way to try to find the best parameters in a class is just to do maximum likelihood. This just amounts to finding the parameters theta that tries to maximize the sum of the log likelihood of the data points. There are many reasons that this is kind of the, I guess, like the first kind of way of fitting parameters that you go for. This is because there's various kinds of precise way to say that asymptotically, that is, as the number of samples grows to infinity, this is going to give you the best kind of estimate of the parameters. Unfortunately, for many kind of parametric families of distributions, in particular for many families of generative models you might want to train, it's actually not easy to optimize this objective. So just to keep one particular example in mind, I'm going to tell you about a particular kind of class of distributions called energy-based models. Again, the idea here is sort of fairly natural. So you're gonna parameterize the class of distributions that you're fitting as p theta of x is proportional to the exponential of some energy e theta of x. So these are energy-based models. They're called energy-based models because basically you're kind of parameterizing the energy of the configurations, and then the distribution sort of prefers to put more mass on configurations that have smaller energy. So why do we like this as a parametric class of distributions? You can kind of clearly see this is very generic. You can take just about any family of functions E theta to stick it into this paradigm, and that's going to give you some, parametric class of probability distributions. A classical choice is you take E theta to be, for example, a neural network where the theta are going to be the weights of the network. So that's kind of on the pro side. On the con side, a lot of tasks that you might want to do with this class of distributions are kind of computationally challenging. For instance, if you want to draw samples from the distribution, there isn't really like an obvious way to draw samples from the distribution. And the typical way that you do it is you set up some kind of Markov chain, typically something that's inspired by Langevin dynamics, which I'm going to mention in a little bit. And then you run this Markov chain for a while, hopefully until something close to convergence. And that gives you samples from something like the distribution p theta. As it turns out, training them is challenging for the same reason. If you kind of write down the maximum likelihood objective and you try to optimize it, and then you try to, let's say, optimize it with some first order method, so you want to try to calculate gradients of the likelihood, what you will easily see by a short calculation is that the gradient of the log likelihood of a data point can be written as the gradient of the energy function, which will be typically easy to calculate. Maybe like, if E theta is a neural network, this is just like, calculated by back propagation. However, there's another kind of term, which is the gradient of the log partition function. And unfortunately, the log partition function doesn't have a kind of nice formula to evaluate in an efficient manner. In fact, if you do a little bit of a rewriting, you can see that the gradient of the log partition function can be rewritten as the expectation under the current distribution p theta of the gradient of the energy. So maybe the most straightforward way to do this is to try to set up some kind of Markov chain Monte Carlo type of approach where you try to draw samples from something like p theta and then approximate this expectation in a Monte Carlo fashion. Okay, so energy-based models, in fact, have a fairly long history. Arguably, one of the first sort of generative models that worked on any kind of even relatively simple images were what are called restricted Boltzmann machines. These are kind of energy-based models where the kind of energy is inspired by a type of undirected graphical model called Boltzmann machines or Ising models, depending on which community you come from. And they were, in fact, trained using this recipe that I had on the previous slide, which is basically maximum likelihood, plus the kind of the sampler that you use to try to draw samples from p theta is like is a common Markov chain called the Gibbs sampler. Subsequent versions changed the energy function to be something parameterized by a neural network. And in fact, it took a relatively long time, and it's like a relatively modern result to kind of scalably manage to train using maximum likelihood this kind of energy-based model. This was arguably first done in a paper by Du and Mordach, where again, they used this recipe of using maximum likelihood plus a particular type of Markov chain, which is based on this Langevin Markov chain, which I'm going to mention in more detail in a couple of slides. What started happening around the same time is that people realized that there's another kind of route you can go to, which is all of these difficulties that we have with maximum likelihood could plausibly be avoided if you just, instead of trying to fit the model using maximum likelihood, you just try to fit it using some other objective. And people realized that objectives like score matching and noise contrastive estimation are viable candidates for these kind of families of distributions, which are specified up to constant proportionality. And the kind of this was nicely done for neural nets scalably in a paper by Song and Herman. The original kind of objective was proposed by in a seminal paper by Apo Hyvarinen in the early 2000s. And then people sort of figured out how to take these losses and take some kind of annealed versions of them and take them to some limits. And in some ways, this was the genesis of diffusion models, which are kind of the de facto state-of-the-art generative model in many areas having to do with generating images. Okay, so this is kind of a very short history. So I'm going to talk about a particular kind of approach here, which is these kind of score-based losses. So maybe let me tell you the most sort of simple incarnation of this paradigm. So this is sometimes called just score matching. So the idea is basically the following. The difficulty with maximum likelihood was that you had this kind of partition function that was causing difficulties with optimization. So the idea is to try to fit an alternate loss which somehow avoids having to talk about a partition function. And the idea is to instead try to fit what's called the score of the distribution. So the score of the distribution is the gradient with respect to the input of the log probability. So for instance, you could try to fit it in like the L2 sense, which would give rise to the subjective that I have on the screen right now. And like, if you want to visualize it, the score is a vector field at any point in space. It's going to give you sort of the direction towards which you kind of expect the probability mass to be increasing. There's a question in Q&A. somebody want to unmute, or Sophia, if you want to read off the question?
The question asks, is it possible to have the slides?
Oh, yes, I can share this. I mean, you tell me. I'm happy to share the slides in some shape or form. However, they're easily distributed to participants.
Okay. I wonder if you put your slides on the website. If you're not, you can send me a
Okay,
call. Then.
I'm happy to do that. Yeah, I'm happy to do that. I
Okay.
can put them on my website.
Okay.
Yeah, yeah,
Okay. Thank
yeah,
you very
yeah,
much.
yeah. Okay. So okay, how do we do this? I mean, this is all nice and good. In particular, you can easily notice that if you look at the gradient with respect to the input of the log probability, because the partition function doesn't depend on x, the gradient with respect to x of the partition function is just 0. So the above expression doesn't actually have partition functions appearing anywhere. So that's kind of good. There's something else there's something else that's bad. So the bad thing is, if you kind of think about how you would try to fit this loss from data, it's an expectation over p data. So fine, I can sort of use the empirical expectation over samples from data as a proxy for this expectation. However, there's this term that's the gradient with respect to x of log p data of x. And of course, I don't know p data of x. That's the thing that we're trying to learn from data. So how do I actually evaluate this term? So this was kind of the main idea in this original paper by Havarinen. So the idea is that you can do a kind of clever integration by parts trick, when this version of score matching is sometimes called implicit score matching in the literature. So what you basically do is you kind of expand out the square. So if you take the square and expand it out, there's going to be three terms, right? Like there's the square of the first term, the square of the second term, and the cross term. And then you see that the first and second terms are not a problem. The first term is an expectation under p data of something that only depends on p theta. So you can easily write down the empirical version of this given samples from data. The second term doesn't depend on theta at all. The only kind of term that still causes some issue is this like third term. Let me get my pointer. It's this third term, because it still has this like log p data of x kind of term inside it. But what you can kind of do is, assuming some like, suitable decay at infinity, you can use integration by parts, and you can kind of move one derivative from log p data onto grad x log p theta, and you can sort of see that this cross term can be written down as the expectation under p data of two derivatives of log p theta, so of the trace of the Hessian of log p theta. And now you're kind of all set. So basically, this loss can be equivalently rewritten as minimizing the sum of kind of two terms, each of which is an expectation under p data of some term that only depends on p theta. And now, of course, if you only have samples, you can parameterize this score, which is the gradient with respect to x of log p theta, by your favorite kind of like, parametric class. And then you can approximate this expectation by its empirical counterpart, so the kind of the average over the training data points. So this is the kind of basic idea behind score matching. Of course, you might, this was, as I said, proposed in this, originally in this paper by Havarinen, and in this paper, he also showed that under some kind of technical conditions, this estimator is consistent. So you might wonder, okay, suppose that I manage to estimate the score, how do I actually now draw samples? Remember, the way that we use the generative model ultimately is like after we've trained it, we want to produce new samples from it. So the way that you do it is by, unfortunately, running a Markov chain. However, now this Markov chain only needs to be run at inference. So when you're trying to draw new samples, it doesn't need to be run when you're training the model. So that's a big saving. So what is the Markov chain? So the Markov chain is this there are typically versions of this Langevin dynamics, which I mentioned a couple of times. So let me tell you what is kind of the basic idea here. So Langevin is a sort of classical Markov chain or diffusion, if you're comfortable with it, to draw samples from a distribution that's parameterized up to a constant of proportionality. So if you have some distribution p theta of x proportional to the exponential of minus e theta of x for some energy function. The way that you can set up a Markov chain to try to draw samples from this distribution while not having access to z theta, of course, is as follows. What you do is you basically run something that looks very similar to a noisy version of gradient descent. So if you're currently at some point xt, what you're going to do is you're going to move in the direction opposite of the gradient of the energy. So this looks just like a gradient descent step. And then you're going to inject some appropriate amount of Gaussian noise. And it turns out that you sort of scale the Gaussian noise to be square root of 2 eta times the sample from a standard Gaussian. So where eta is sort of some analog of a step size here. And then what it turns out is that if you take eta to go to 0, the appropriate limiting object here is what's called the stochastic differential equation. If you don't know what it is, don't worry about it. It's not going to matter too much for the rest of our talk, but it's some object that looks like this. Is basically the point xt changes with some deterministic drift opposite of the gradient of the energy function, and then you inject some amount of Brownian motion. So if you wish, if you're more comfortable with optimization, this is the sort of the relationship between this and the previous equation is the same as the relationship between a gradient flow and gradient descent. One is a discretization of the other. And the nice thing about this stochastic process or Markov chain, however you want to think of it, is that if you let it run to convergence, it's going to, under some mild conditions, converge to the distribution you're trying to draw samples from, which is the distribution p theta proportional to the exponential of the negative of the energy. So if we actually manage to estimate a score, which is kind of close to the intended score of the data distribution, what you do is you just run this Markov chain. So basically at any point in time, you sort of move in the direction of the estimated score, you inject the appropriate amount of Gaussian noise, you run this for a while, and that's basically it. And of course, the kind of error analysis here is non-trivial, but it's going to be orthogonal to what I'm going to talk about in the talk. But there's quite a bit of recent work on trying to do kind of like error propagation analysis, which tries to say, oh, like if I have some amount of error in the score, how does it propagate to the actual, like in some distance measure of the distribution that I'm producing samples from. Okay. This is kind of the nutshells of score matching, and sort of if this process is done kind of successfully end to end the way that I described it, this is kind of how drawing a sample looks. You sort of start with something like random Gaussian noise. You run this Markov chain for a while, and as you run it, it starts to look progressively more and more like a sample from the distribution. On the left, it's some distribution of faces. On the right, it's some distribution of kind of natural looking images. Okay, so here's the question that I'm going to care about in this talk. So remember kind of what was our thought process in trying to derive this score matching objective. We like maximum likelihood, and the reason why we like maximum likelihood is that in many ways it's sort of statistically the gold standard. It gives you basically the asymptotically optimal kind of error in the sense of, like, let's say the expected square error of the quality of the parameters that you're estimating among all nice enough estimators. Again, if you know, there's a variety of kind of versions of this claim. Maybe the most famous one is the Hayek-Lecam theorem. If you don't know, it doesn't really matter. Think of it as this is the gold standard. Asymptotically speaking, it gives you the best kind of quality of estimation in terms of expected square error. On the other hand, we chose score matching because it's sort of it gave us a way to circumvent some computational difficulties with maximum likelihood. So the question is, what did we lose in this exchange? So we gained something algorithmically. Now we can fit the parameters more efficiently. What did we lose statistically? So we want to know how suboptimal is it compared to the maximum likelihood estimator. So let me start with some kind of easy empirical observations. Some were observed in this very nice paper by Song and Hermon from 2019. So basically, you can kind of very easily convince yourself that if you have some distribution that, let's say, looks multimodal, what you're going to get when you receive samples from this distribution is you're going to get a lot of samples close to the modes. So here, the bottom left and the top right, but not a lot of samples sort of somewhere in between. So probably the score is not going to be estimated very well in between, probably better close to the modes. And so the worry is, like, if, how does this propagate to the quality of the distribution that you're estimating? In fact, in the 1D case, you can do this pretty much explicitly. So in the 1D case, what you can do is, because you have fundamental theorem of calculus in one dimension, if you have the score is related to the PDF of the distribution by calculating an integral by fundamental theorem of calculus. So what you can do is the following. You can take a mixture of two Gaussians in 1D, and you can try to gradually modulate the separation between the two means, and you can compare the quality of the PDF that you get with maximum likelihood, say, and with score matching. And so what I'm showing you on this figure is maximum likelihood is basically the ground truth. This is sort of like it's an easy enough distribution, and there's enough samples that you can think of the green curve, which is maximum likelihood, as just the correct distribution. And then blue is what you get with score matching after you do fundamental theorem of calculus. And what you can do is, the more separation you have between the modes, the more kind of the worse score matching is compared to maximum likelihood. In particular, you can see here that the kind of relative magnitude of the modes is severely wrongly estimated. And this was kind of proposed as a explanation in this paper by Song and Hermon. But unfortunately, there's some kind of worry that in high dimensions, it's not clear what causes this phenomenon, in the sense that there might be many reasons why you might have gaps in the probability distribution, kind of regions of low probability. Maybe the distribution is supported on some low-dimensional manifold. Maybe it's multimodal, like in the mixture of two Gaussians case. Who knows? So it's not entirely clear what causes the problem for score match. All right, so part one. This was kind of in a sense like a long preamble. So let me tell you in the first talk, a kind of basic template that tries to understand what are the obstructions for score matching having a good statistical efficiency. So let me just start with the main message. So the main message is basically going to be the following. So there's going to be a surprising connection between the algorithm that you're using at inference time, so the algorithm that you're using to produce samples from the trained model, which is this Langevin dynamics Markov chain, and the statistical efficiency of the score matching loss. Now, this is surprising because these two tasks, although like they're both things that you care about, one is how efficient is the estimator, the other one is can I draw samples computationally efficiently, they a priori have nothing to do with each other. However, it turns out that what you can prove is that if you, roughly, informally, you can prove that score matching is comparably as efficient as maximum likelihood if the Langevin Markov chain mixes rapidly. Roughly, what we're going to show is that if you look at the squared error of the score matching estimator, it can be roughly written down as the squared error of the maximum likelihood estimator times some quantity that characterizes the mixing time of Langevin and times some other nuisance quantities that characterize sort of the niceness of the score in terms of some smoothness properties. Okay, so let me try to make this a bit more concrete. This is a stats audience, so maybe the easiest kind of warm-up example that I'm going to start with, although almost everything I'm going to say holds beyond exponential families, is exponential families. So what is an exponential family? It's a very simple example of this energy-based paradigm where the distribution p theta of x is proportional to the exponential of an inner product between some vector theta and some sufficient statistics f of x. So one kind of obvious example you might think of is like, if f of x, say, contains the monomials of degree 1 and 2, this is going to be a Gaussian. You can, if you're kind of coming from more of a machine learning background and you're kind of more used to classification, the same way you think of kernels as basically having fixed features and you're training a linear function over these features, you can think of this in the same way. You can think of the f of x's as sort of features, and then you're trying to fit like weights data over these features. Okay, so let's do some simple observations. Even in this very simple family, if you try to do maximum likelihood by sort of the expressions that I showed you previously, if you're trying to optimize it with, say, a gradient-based method, you need to be able to draw samples from p theta. And unfortunately, it turns out that, as I'll show you in a little bit, even in this very simple case, even if these f's are something very simple, like low-degree monomials, sampling can be computationally hard. So unfortunately, MLE is computationally hard to fit. On the other hand, the score matching estimator, in fact, is so simple here that it even has a closed form. The score matching loss turns out to be a quadratic, and the optimum of a quadratic can be explicitly written down. It's basically something like what I'm showing you here on the screen. Doesn't really matter what it is, but the only point is it's some closed form expression that you can calculate from the samples. So it's super easy and super efficient to calculate. Okay, so now let's try to compare the statistical efficiency of the score matching estimator and of maximum likelihood. So I'm going to focus on the asymptotic analysis case here. So I'm going to look at the asymptotic efficiency of the two estimators, though in the paper we have quite a bit more even in the finite sample case. So let me introduce just like small bits of notation. So I'm going to call sigma x to be the covariance of some random vector x. And then some things that I'm sure we all know. Maximum likelihood under some very mild regularity conditions, certainly some that are obtained for the exponential family case that I'm looking at, is going to be asymptotically normal. And what it means is if you sort of appropriately scale the difference between theta hat MLE and theta star, it's going to go to a mean zero Gaussian with some covariance matrix. And the covariance matrix is basically the inverse of the covariance matrix of the Fs. Also, you can also known as the inverse Fisher information matrix. Turns out score matching is also asymptotically normal. of course, with a different covariance matrix. So here I'm calling it gamma SM. So the expression is a little bit ugly, but I'm showing it to you here anyway. So what you can see in the expression is like it's a product of three matrices, the first and the third of which are the same. The first and third matrix look like sort of like a covariance, but instead of the sufficient statistics, derivatives of the sufficient statistics. So J denotes here Jacobian. So this is expectation of Jacobian of the sufficient statistics, Jacobian transpose inverse. And then in the middle, there's some matrix, which is roughly the covariance of some quantity that looks like some matrix times the theta star and plus like, the Laplacian of the sufficient statistics. So the main point I want you to sort of focus on here is that the first and third matrix look very similar to the Fisher information matrix, apart from one extra derivative, because the score-based laws is trying to fit like, the score of the distribution. When you go through the calculation, you can see that the first and third matrix look like expectation Jacobian F transpose. And here you have something that looks like expectation FF transpose. And I'm not going to show you how this is derived because it's very sort of straightforward. It's just you kind of look at the standard expression for what the if you have an asymptotically normal estimator, you can write down what the covariance matrix is in terms of the the Hessian of the loss and the covariance of the gradient of the loss, and just go through the calculation, and then you'll see it looks like this. So now if I want to, in the asymptotic sense, compare the efficiency of score matching and maximum likelihood, I need to, in some sense, just know how much bigger gamma SM is compared to gamma MLE. So I'll tell you that, but maybe before I do that, just a couple more bits of definitions and notation. I'm also going to need this constant of a Poincare constant. So the Poincare constant of a distribution is the smallest constant, such that for any smooth function, I can upper bound the variance of that function by the constant times the expectation of the gradient of the function. If you've never seen this before, it will almost certainly look quite odd. The reason why this crops up is that it's very related to the spectral gap of the generator of the Langevin diffusion, which if you're more kind of comfortable with discrete Markov chains, it's some kind of analog of the Laplacian for a random walk over a graph, and it characterizes the mixing time of the stochastic process in a particular type of distance called the chi-squared distance. And I'm also going to need a restricted Poincare constant, which is a less familiar concept. Like we introduced this in our paper. So this is the same quantity, except rather than looking over all smooth functions, you look at a restricted class of functions, namely functions which are linear in the sufficient statistics. So they have the form tau times f of x for some vector tau. And of course, because you're looking at a smaller class of functions, this constant is certainly going to be smaller than the Poincare constant. How much smaller? Stay tuned. Note that this Poincare constant, because it characterizes the mixing time of Langevin, in particular, it sort of naturally captures some obstructions that I showed you in the empirical observations. For instance, if you have a multimodal distribution, like a mixture of two Gaussians with means at, let's say, -a and variance 1, then the Poincare constant is exponentially large in a squared, meaning if the means are kind of further and further separated, so like if the distribution is more sharply multimodal, the Poincare constant will be bigger and bigger. Okay, so this is the result we prove. So the result we prove is that we can upper bound the operator norm of the gamma SM matrix. So you can think of this as the efficiency of the score matching estimator by the restricted Poincare constant squared times gamma MLE operator norm squared, so the efficiency of maximum likelihood, and then plus some nuisance term, which looks like some moments of the derivatives of the sufficient statistics. So this captures some notion of smoothness of the sufficient statistics. So what does it say? The left-hand side is the efficiency of score matching. You can upper bound it by, roughly speaking, the efficiency of maximum likelihood times something that characterizes mixing time, the Poincare constant, times some smoothness-like quantities. I'll show you sort of the main core bit of the proof here, but maybe if you sort of intuitively want to kind of like convince yourself that maybe quantities like this appearing is not too crazy. This is not how the proof works, but this is just like purely for some kind of rough intuition building. You can think of the kind of Langevin as being some kind of stochastic fundamental theorem of calculus. It's like an iterative method to take the estimated score and convert it to a distribution. And the longer the kind of the mixing time, the more steps you need to take. So maybe the more you would you would imagine that error will accumulate. And then the smoothness term is sort of something that will characterize some notion of complexity. So kind of usually when you have generalization bounds, you have appearing certain quantities that will track some notion of complexity of the class, so you can expect smoothness here to appear as some notion of complexity. So as I said, this is just purely for some kind of rough intuition building. Let me tell you what is sort of the main kind of ingredient in the proof of this. But maybe before I do that, let me also kind of make a couple of quick remarks. So remark one is that in some qualitative sense, some dependence on the Poincare constant and on smoothness is required, although the precise dependence is probably loose. So we have some lower bound to this effect. And you can, from this, very easily extract some kind of with constant probability bounds on the differences of on kind of the quality of the estimator. So basically you can say with probability 99% or something, let's say the appropriately scaled squared error of the score matching estimator is at most the appropriately scaled squared error of the maximum likelihood estimator times times all of these constants, like the Poincare constant and the smoothness constants. Okay, so let me tell you now what's the main ingredient for this result. So if you'll recall, the gamma SM matrix has these three matrices. So one, the first and third matrix are basically this sort of these matrices that look like the inverse Fisher matrix, just with this extra one derivative. So as it turns out, the sort of middle term is, the middle term is very easy to upper bound. So basically you can use just some triangle inequality to relate the covariance matrix of a sum of two things to the sum of the covariance of the two things. And then these sort of smoothness-like terms pop out from just some very simple kind of algebra and triangle, essentially just like repetitions of triangle inequalities. The biggest worry are the first and third matrix because there's an inverse showing up there. And so the worry is that these matrix could be sort of much close to singular than, let's say, the expectation FF transpose, which is what you get in the inverse Fisher information. So this is the main lemma. So the main lemma is that you can relate the first and third matrix. So you can relate expectation JF transpose inverse to the inverse Fisher information matrix. So you can prove that it's at most in the PSD sense, the restricted Poincare constant times sigma F inverse. Okay. So let me show you how this works. So basically the proof is going to go as follows. I'm going to take some arbitrary vector W, some arbitrary direction W. And then I'm going to look at the quadratic form of evaluating expectation JF transpose in this direction W. So I'm going to look at W, inner product expectation JF transpose times W. By linearity of expectation, this is the expectation of the gradient of inner product W f of x, norm of that squared. This is just putting in the W's inside of this expectation. And now you can see how this is starting to look like something that the Poincare inequality is suited for. This is the expectation of a derivative of a function. I can relate it, if I'm willing to lose the Poincare inequality, to the variance of the same function. So this is bigger than or equal to 1 over the restricted Poincare constant of the variance of W f of x. And then this is nothing but evaluating the covariance matrix of the f's in the direction of W. And so what did I prove? I just proved that expectation JF transpose is bigger than or equal to 1 over CP sigma F. And then by monotonicity, what I know is that the inverses of that are basically follow. So expectation of JF transpose inverse is less than or equal to CP times sigma F inverse. And that's the entirety of the proof for this lemma. Any questions up to this point?
Yes, there is indeed a question from the audience. Can you see that, Andrej, or I can read it to you?
If you could read it off, it's probably better. Yeah.
Okay. Yeah. Are the results contingent upon using Langevin dynamics to sample from P theta? Will anything change if Hamiltonian dynamics was used instead?
So the statement here is purely about the efficiency of the estimator. Now, look, it's a very good question why Langevin happens to show up as the relevant Markov chain to characterize the efficiency of the estimator. I'll come back to this in a little bit. Like indeed, it's kind of mysterious why Langevin sort of popped up, because I'm not talking about efficiency at all of sampling. I'm just talking about statistical efficiency. It is very mysterious, and I'll come back to it. Okay, good. So let me maybe skip this in the interest of time. It turns out that there's a lower bound, and let me skip over it. As I said, this is exponential families was kind of nice to make my notation a little bit easier for the slides. This sort of same result also holds if you're willing to assume that the estimator is asymptotically normal, and then sort of similar type of result is going to hold, except every time you have an f, you'll instead have gradient with respect to x of log p theta. So it's basically more or less the same kind of calculation, and the result is what I'm showing you here. Okay, so now this was the most basic kind of part of the framework. So now let me show you a little bit. So I kind of made a point to tell you that this restricted Poincare constant is smaller, but how much smaller is maybe not so clear. So let me show you like a kind of pretty nice result, in my opinion, that that shows you that like the restricted Poincare constant can be sometimes in very natural circumstances much smaller than normal Poincare constant. So here's some easy sort of simulations. So what I'm showing you here is basically you're trying to use score matching to estimate a distribution that looks like this. So this is some distribution which looks bimodal. It's even though it looks very similar to a mixture of Gaussians, it's actually not. It's basically like a proportional to the exponential of some degree 4 polynomial, and then like the minus a and a tell you like where the bumps lie. So basically they give you sort of like roughly the means of these two kind of like components. And you can try to fit this distribution with two different sufficient statistics. So, or two different families of sufficient statistics. In one of them, you view this distribution as a member of a sufficient statistics family, where one of the sufficient statistics has the following form that I'm underlying here. It's not entirely important what it is. What is important is that one of these sufficient statistics has this ERF function. So this is the error function. And this function kind of looks like a cut in this distribution. So it basically looks like a smoothed cut that sort of puts most of the value kind of on separating the two components in this bimodal distribution. And if you look at the plot, you can see that the larger I make the distance between the two means, like so the larger A is, the more kind of inefficient score matching is. So the worse the error is for estimation with score matching compared to MLE. However, if I make the sufficient statistic family nicer, so I basically remove this like, sufficient statistic that had like, this ERF function that traces a cut, and instead I have just a sufficient statistic that is some like, degree 4 polynomial, which is sufficient to contain this distribution. You can see that even if I make A very large, so like on the x-axis, I'm still representing the magnitude of the A, even if I make it very large, the two estimators are basically on top of each other. There's not a big difference. So it turns out that this is a very general phenomenon. So what we can show is the following. If I take an exponential family, and if I think of these f's as being, let's say, all non-constant monomials of some bounded degree, so let's say degree at most little d, and some bound on the sufficient statistics, say in the L infinity sense, it's at most b, and there's also some base measure to make sure that this is like, this is a well-defined probability distribution. It's gray, it's pale grays because you don't have to worry about it too much. Then what we can show is that for this very kind of general family of distributions, you kind of almost get only wins from score matching and no losses. So what I mean by that is that the statistical efficiency of score matching is basically only polynomially worse than MLE. In particular, it's only NB to the power poly of D worse. So if you think of little d, the bound on the monomials as like a constant, this is polynomial in the ambient dimension, which is N worse than MLE. And moreover, because this is an exponential family, it's of course computationally efficient. It just boils down to evaluating the minimum of a quadratic. By contrast, if you're trying to do this with maximum likelihood, in particular with the first order oracle for maximum likelihood, it's in fact intractable to do this. So implementing a first order oracle is in fact NP hard, or to be more precise, you cannot do it unless NP is equal to RP. So this is kind of an analog of some very nice results that have been showing up in the kind of graphical model literature for discrete distributions. So in Ising models, people have shown that there's a kind of a similar separation where there's classes of Ising models over graphs with bounded degree that can be learned computationally efficiently with some other method that's not maximum likelihood, even though maximum like basically solving the maximum likelihood objective happens to be computationally intractable. And perhaps even nicer, some of the algorithms that people used here are some kind of close relatives of pseudo likelihood, which are in terms some kind of close analogs of score matching in the discrete world. If you don't know what pseudo likelihood is, don't worry about it. This is just kind of a remark for the kind of experts that might know what these are. In case you care about the precise statement, you could probably infer it, but basically the result roughly says the following. The score matching estimator will satisfy, like, with some, let's say, 0.99 probability. If you look at the error of the score matching estimator, it's going to be something polynomial in n, so nb to the poly of little d, divided by the number of samples capital N. And in fact, if you compare the sample the operator norm of gamma SM and the operator norm of gamma MLE, so the asymptotic efficiency of score matching and maximum likelihood, they'll be off by the same factor, NB to the poly of D. And moreover, maximum likelihood is provably intractable to implement in a precise sense, meaning unless NP is equal to RP, you cannot have an oracle which runs in time polynomial in the ambient dimension that can implement the first order oracle, meaning that at particular, at given points theta, it gives you, say, the value of the gradient of the maximum likelihood loss at that point theta. And this is true even for some very small little d and capital N. So little d can be just like 7 or something. So this is sort of like you don't need to let like little d grow. You can just take it to be a constant. The way that you prove this is basically by proving that the restricted Poincare constant is good. So basically upper bound for any function f, which is linear in the sufficient statistics, you bound the ratio between the variance and the expectation of the gradient of that function. And you can prove that it's basically roughly something which depends on the condition number of the Fisher information. I will not show you the proof of this, but maybe I'll just say a word, which is why low degree polynomials happen to be useful here. The reason is if you look at this expression, it involves f and derivatives of f. And polynomials have this nice property that they're kind of downward closed in the sense that if you take a derivative of a polynomial, it's going to be another polynomial of lower degree. And so in some ways we can kind of, because the sufficient statistics are all of the monomials up to some degree, having this property is nice because we can kind of talk about various expectations and moments of these quantities and derivatives thereof. And the way that you derive the result is like all of the kind of quantities in green, you can end up bounding them in terms of the kind of quantities of interest, which is capital B. This is the L infinity bound on the parameters, little d, which is the maximum degree of the monomials, and little n, which is the ambient dimension. Okay. So moral of the story was that the restricted Poincare constant can be substantively smaller than the Poincare constant. So this kind of distinction can buy you quite a lot sometimes without losing anything. Any questions on this
part? So far, not I can see from the Q&A session. Maybe some at the end.
Sounds good. Okay, so next part, and I was very nicely set up. Somebody asked me before why somehow, what gives with Langevin? Like why somehow this statistical efficiency happens to be related to the mixing term of Langevin? Why not Hamiltonian Monte Carlo? Why not anything else? So this kind of baffled me for a while. And eventually we discovered something very nice. So it turns out this kind of, my talk didn't have just score matching in it. It had score losses. So it turns out that there's nothing special about Langevin. There's something special about the link between Langevin and score matching, but there's a very nice dictionary between the mixing time of just about any time homogeneous diffusion you would like to pick, and the statistical efficiency of not score matching, but something called a generalized score matching loss. So this is some generalization of the score matching loss. And the type of theorem that we can prove is going to show up in the upcoming quote is that basically for most time homogeneous, for most nice time homogeneous diffusions, there's some corresponding generalized score matching loss such that a similar result to what I showed you hold. if you look at the quality of this generalized score matching estimator, you can upper bound its statistical efficiency by basically the efficiency of maximum likelihood times something having to do with the mixing time of the diffusion that you picked times the sort of some notion of smoothness again. So this looks in a pattern matching sense, it looks exactly identical to what I showed you. So what is generalized score matching? So a generalized score matching loss looks like following. You pick some linear operator O, and then instead of trying to match the gradient of log P, what you're going to try to match is OP divided by P for any choice of operator O. Now, if you pick O to be the gradient with respect to the input, what you can see is that you get gradient of P divided by P, which is gradient of log P. So you just recover standard score matching, but this works for any operator O that you like. And then the result basically says, if you choose your O such that it's basically the square root of the generator of the diffusion of any diffusion that you like, and that diffusion has a Poincare constant CP. So again, think of this as the mixing time of the diffusion. Basically, the same result holds. So you can upper bound the operator normal of the corresponding generalized score matching estimator by the Poincare constant of this generator times the efficiency of maximum likelihood, times some terms that have to do with the smoothness of now, not like the normal score, but this notion of score. So instead of having terms that look like grad log P, you're going to have terms that look like O log P, or OP divided by P. Okay, why is this nice? This is a very nice dictionary now, which basically allows you to take all of the kind of textbook ways that we know how to speed up Markov chains. So for instance, preconditioning or tempering, and translate them to better losses. So for instance, when we do when we do sampling by Langevin, like one of the things that we know can speed up the mixing time is preconditioning the gradient by some appropriate matrix. Again, if you come from optimization, this is also should be no surprise to you. Oftentimes the way that we speed up gradient descent is like by kind of preconditioned versions of gradient descent. In fact, it turns out that there's a very nice characterization theorem due to Ma et al., which says that if you fix some distribution P of X as a target stationary distribution, basically any sufficiently nice diffusion can be, I guess the precise term is Ito diffusion, but think of it as a time homogeneous diffusion, can be written in the following kind of form. So if you look at this, it looks like preconditioned Langevin. So basically the block terms look like dxt is minus grad f plus square root 2 of dbt, that's just Langevin. And then what you do is you can inject this matrix D, which is like a preconditioner for grad f. You need to appropriately precondition the Brownian motion as well. And then you need to correct with this gamma matrix in the drift to make sure that the stationary distribution is preserved. But think of this as some way to take Langevin and basically precondition it. And allowing arbitrarily nice preconditioners basically gives you just about any homogeneous diffusion to sample from P. And lo and behold, if you write down the corresponding generalized score loss that corresponds to this this diffusion, it'll look like exactly like the standard score matching loss, except it's preconditioned. So basically, the same preconditioner that shows up in the diffusion is going to show up as a preconditioner in the score loss itself. So rather than fitting grad x log p minus grad x log p data, now you're fitting square root of the preconditioner grad x log p minus grad x log p data. So as I said, another strategy to try to speed up Markov chains is what are called tempering heuristics. So these are loosely speaking heuristics in which what one does is one runs a Markov chain over an augmented space where there's another added random variable called typically temperature. And so what you try to do is you try to change the temperature or the position of the Markov chain. The idea being that at higher temperatures, you will have somehow faster mixing by trying to sample from a distribution which is flatter. Interestingly enough, in the very first paper by Song and Armon, they introduced the following anneal strategy for score matching. So what they said is like, okay, somehow we seem to be having problems in multimodal distributions. Why don't we, rather than just trying to fit the score of the original distribution, try to simultaneously fit the score of a bunch of versions of the data distribution convolved with different amounts of levels of noise. So why don't we try to fit P sigma I data for a bunch of sigma I's where these distributions are P data convolved with a Gaussian of mean 0 and variance sigma I. The intuition is supposed to be that the larger sigma is, the closer the distribution gets to like a unimodal Gaussian. So it should be easier to estimate the score. And somehow estimating the score at the higher noise levels should help you estimate the score at the lower noise levels. And the way you turn this into a loss is kind of maybe straightforward. You essentially have the score losses for each of the different sigma i's. You weight them appropriately, and then you sum them up. And these lambda of sigma i's are some chosen relative weights for the different noise levels. The reason why you choose, let's say, convolution as a way to make the distribution easier is because you can easily produce samples from this. If you have samples from P data, the way you produce samples from P sigma I data is you just draw a sample from P data, you draw fresh Gaussian noise, you add the noise to the sample from the data, and that's your sample from the convolved distribution. Also, interestingly enough, the way that they thought of this strategy in the Song and Hermon paper is that they thought of this as a kind of double fix. They thought of it like it should somehow help the score loss estimation, but it should also help at inference time when you're trying to draw samples. I mean, we all know that local Markov chains like Langevin can take a very long time to mix when you have very multimodal distributions. So for instance, if I have a distribution whose score looks something like this, so there's two very sharp minima, there's kind of classical results from analyzing metastable processes, for instance, the kind of seminal results by Bovie in the early 2000s that tells you that if you want to go from A to B through C, you have to wait time that's exponentially long and the kind of difference of the score between A and C. But now, this kind of dictionary that I told you that allows you to think about score losses and their statistical efficiency in terms of Markov chains and their mixing gives you sort of license for why you can kind of conflate these two things and think of this kind of tempering or annealing type of strategy as a double fix, both for sampling and for statistical efficiency. So what we show is that if you look at a lifted stochastic differential equation, meaning if you look at running the Langevin Markov chain on a distribution which is not just over x, but over x and an added variable beta. So this beta is going to correspond to the amount of Gaussian convolution that you add. And the stationary distribution that we're going to run Langevin for is the one where you first pick a temperature or amount of noise by some weighting probability R of beta. And then conditioned on beta, you sample from P beta of x, which is the convolved distribution P of x with a Gaussian of covariance beta identity. Now, if you think about running Langevin on this lifted SDE, because of this extra temperature parameter, P beta for, let's say, very large beta is going to be much easier to sample from. It's going to be a flatter distribution, so it's going to look like something like the kind of the rightmost end of this picture, even though the original distribution might look like a bimodal distribution, like what's on the leftmost side of this picture. And Langevin kind of will change both the beta and the x, so it'll kind of allow you to leverage the faster moving in this landscape at the higher temperatures to achieve a better mixing time for both the higher and lower temperatures. If you write out the corresponding generalized score matching loss that corresponds to this lifted stochastic differential equation, guess what you will get? You will get something that looks very close to this annealed score matching loss that I showed you before. So it'll look like a weighted average. So you're weighting over the different betas with magnitude R of beta. The standard score-based loss, but for the beta annealed distribution. So basically the expected kind of squared error of the estimated score for the distribution at temperature beta, basically with convolution amount beta between the true distribution and P theta. And then unlike the sort of standard empirical loss that I showed you in the previous slide, there's kind of a higher order correction term from this SDE. So there's like another term which basically kind of corresponds to trying to match the scores, match one more derivative of the score. So these terms look like differences of traces of the Hessian of log P. So that's sort of like a kind of second order correction. And also what it turns out is that if you have even relatively benign assumptions on the data distribution. So let's say the data distribution looks like a mixture of Gaussians with a shared covariance. Then this sort of like lifted SDE, which we call continuously tempered Langevin, continuously tempered because it's like a tempering heuristic, but the tempering kind of is continuous in the sense that there's a continuous number of temperatures. It turns out that even for cases where the means are very well separated, so that Langevin mix is very slow, this tempered Langevin mixes actually very fast. So it mixes in time, which is polynomial in the ambient dimension and all other parameters of interest, diameter of the means, minimum of the maximum of the eigenvalues of the covariance. And it turns out actually without even any dependence on the number of components in the mixture. So this is a relatively this is a relatively minor assumption because of kind of universal approximation style results, which tell you that even kind of that basically you can approximate just about any nice enough distribution by a mixture of Gaussians if you take the kind of the variance to be small enough, and because this sort of result doesn't depend on the total number of components, in a way this is a kind of pretty general statement. Of course, this is a purely statistical statement, so kind of algorithmically speaking, solving these objectives is going to get very hard for distributions that look like this, but at least statistically speaking, there's no kind of obstacle. Okay. So this was kind of what I wanted to say kind of in terms of prior results. Maybe let me just wrap up by telling you some kind of open directions and things that I'm very excited about. So I talked mostly about continuous distributions and score-based losses as kind of ways to fit these kind of continuous space distributions. There's quite a bit of interest in trying to understand discrete analogs of these losses, in particular because there's quite a bit of interest in trying to get better diffusion models that operate for discrete distributions. So these are sometimes called discrete diffusion models. And recently, I've been kind of working with a bunch of my students and some collaborators at Google on trying to do kind of do parallels of this theory for discrete space. And in particular, somehow there's also a nice picture emerging here that says that in some ways, pseudo-likelihood-like losses, which are sometimes called in the kind of language modeling literature, masked language modeling losses, they have a connection also to their statistical efficiency has also a connection to particular types of Markov chains. Here, it turns out they're kind of some general class of Gibbs-like samplers. So somehow there's the same kind of dictionary going on, except that here what I told you is how to connect score-based losses with diffusions. Here, the connection is between these sort of pseudo-likelihood-like losses and Gibbs-like samplers. I kind of only talked about statistical advantages and statistical lenses on different score-based approaches. There's kind of quite a bit of speculation that one of the reasons why kind of diffusion models, for instance, work very well is because there's some benefits to the optimization dynamics. In particular, we're trying to kind of fit some more gradual objects compared to previous methods like, say, GANs or variational autoencoders. It's pretty much completely open to make any of these sort of like benefits theoretically formal in any sense. So kind of benefits to the optimization dynamics is a completely kind of open field of research. And maybe the most general sort of umbrella here, which is how I got interested in this line of work, is to try to sort of have more formal trade-offs and separations between different training strategies, different families of generative models, and try to understand what are the relative pros and cons so that kind of designing better generative models becomes more of a science and less of a just sort of like trial and error kind of discipline. And with that, let me maybe just leave this slide with the references for the papers I talked about. And thank you for your attention. And I'm happy to open it up for Q&A.